Today's reading is about special systems of linear equations. Taking a closer look into our topic, the word system. You hear the word system in, for example, a solar system. And solar system, it consists of different types of planets, Earth included, and it's a collection of them. So we could reinterpret system as maybe the collection of linear equations. Linear equations, we could think of it as lines. So we're looking at a special collection of lines. Reading goes, when a system of equations consists of two lines that intersect in one point, let's try to draw what that line means. A system of equations consists of two lines, so let's draw a line and another line that must intersect at a point. So I can draw it this way. There will be an intersecting point right here, and that is that one point, as shown in figure 1 below. There is exactly one solution to the system. Let's go ahead and look at figure 1 with my red pen here. This is my figure 1. It's very similar to what we drew here. And in this case, blue and green intersect. The lines intersect at point here, which implies there's that one point is the solution. So what this is implying is that the intersection point is the solution. If two linear equations in a system have the same graph, so how would a graph have the same graph? First of all, let's call this case 1. And now we're looking at a second case where the graph are the same. So if I draw one graph, one line, one linear line, and another line with the orange to be the same, they have to be identical, or they lay on top of each other. So thinking about this case, how many solutions do you think this one will have? How many points on these two lines do they intersect? So let's go ahead and on with going back to the reading. As shown in figure 2, the graph are coincident lines or the same lines. So there's a figure 2 right here with my orange pen. They have one blue line. So what they're trying to tell us is that those are two exact same lines that lay on top of each other. It might seem like one, but there's actually two, so it might be easier to see it over here, the way we drew it with the black and the orange line. There are infinitely many solutions of the system because every point on the line represents a solution of both equations. So there are infinitely many solutions. Going back to the case 1, it says that the solution is when they intersect, right? So let's go ahead and examine point here. That point here, they are the orange and the black line is intersecting. Over here, they're also intersecting here. So every point on this line, there are infinitely many points on this line, they intersect. So which implies there's infinitely many points of intersection. Which is the solution. Okay. A system with at least one solution, at least one means there could be more than one. One solution is a consistent system. So which one had one solution? That one was our case 1. And the case 2 had more than one solution. So case 1 and case 2 will both be a consistent system. And thinking about the word consistent, that means no change. Consistent system can either be independent or dependent. So independent and dependent. I like to think about independent as being parents, where we don't need to depend on anybody. But as far as the dependent would be more of a student who still needs the parents' guidance and support. So dependent is students, and independent are the parents. Okay. An independent system has exactly one solution. So that was case 1. The graph of an independent system consists of two intersecting lines. That's exactly. And the reason why they call it independent, why would they call it independent? Because if I call this line 1, L1, and if I call this line 2, they don't need to depend on each other for them to have an intersecting point. So if line 1 could go in a different rate, and line 2 could go like maybe this way with a different slope. But despite what the slope of the two different lines are, they still guarantee to intersect at a point. A dependent system has infinitely many solutions, so that will be our case too. The graph of an independent system consists of two coincident lines. So they call it dependent because these are L1 and L2. Line 1 has to depend on line 2 for them to be the same. If line 2 is different, then they will not make an identical line. So they need to depend on each other to be the same in order for them to have infinitely many solutions. When two lines in a system do not intersect, this is our new case. So let's label that case 3. This is when they don't intersect. So how would a line not intersect? If I have a line, if I don't want this line to intersect, this will be intersecting. But I don't want it to intersect. The only way for it to not intersect is for them to be parallel, where the distances are equal all along. This distance is equal to this distance. They're the same throughout the line. And this is shown in figure 3. Figure 3 is right here. And as suspected, these are two parallel lines, the blue and the green lines, where let's take a closer look at these two graphs. They have the same, they're going at the same slope. They're rising and running, rise over run, rise over run. They're going in the same rate, but the y-intercepts are different. They intersect at a different point on y-axis. They are parallel lines. There are no ordered pairs. Ordered pair just means a point. A point that satisfy both equations. So there is no solution. There's no solution because they never intersect. They could never intersect. Even if they keep on going, they will never intersect. A system has no solution is an inconsistent system, which is the opposite of consistent, and this has solutions and the parallel lines don't. And the bottom is the breakdown of the 3 cases that we just discussed.